So for these two matrices to be equal, their corresponding elements have to be equal as well. So A11, the first row, first column element, has to be equal to the first row, first column element in the second matrix. A11's value will be -3. A12's value will be -2. A21's value will be 7, and A22's value will be 13. Okay? Addition of matrices. If two matrices are of the same order, remind me, what was order? Four by three, 3 by 4, the row by column, right? If they're of the same order, they have the same number of rows and columns, and we always write the rows first, then they can be added together to form a new matrix. So we also denote matrices often with a capital letter. So this matrix is called A. What's its order? 2 by 3. Here's matrix B, also a 2 by 3. Because they have the same order, we can add the two matrices up. And we do that by adding the individual elements, the corresponding elements. So A plus B will again be a 2 by 3 matrix. Notice we use the square brackets to talk about matrices. And what will be the first element, first row, first column, if we're adding them together? 1. First row, second element. 6. First row, third column. 2. Second row, first column. 2. Second row, second column. And second row, third column. Pretty simple, right? Okay. Orders of our second example here. What's the order of this matrix? 3 by 1. This one is a 3 by 1. When we add them up, we'll get a 3 by 1. First row, first column. Adding them together, what do we get? 3. Then -3 and 2. Nothing earth-shattering there, right? How about the next example? Can't do it, right? Not possible, why not? Right. Okay, because we have a 2 by 3 and a 2 by 2. Okay? Scalar multiplication and matrix subtraction. So you can multiply every element of a matrix by a number called a scalar. Just like distributive property in algebra. Every single one has to be treated, every element has to be treated the same. So we're given a matrix A. That's a 3 rows by 2 columns. And B, a 3 by 2. If they ask us to find -3 times A, we're going to get a 3 by 2. And what's going to be in each of those spots? Multiply each number by -3. So we multiply every single value, every single element by that same number. 2b. Again, a 3-row by 2 column. So my result will be 3 rows by 2 columns. And we're taking 2 times every single element, scalar multiplication. So 0, 8, -2, 6, 2, and 14. Doubling every value. Okay. Now if we wanted 3a plus 2b, we just found 3a, we just found 2b, so we don't have to do it again. We can simply add the 2 together. We'll have a 3 by 2. -3a plus 2b. I take my -12 and 0. Adding 3 to 8. Adding 0 to -2. -12 to 6. 9 to 2. And -24 and 14. Okay. Next slide. Oh, I bet. All right, everybody ready? Okay, here we go. So, properties of matrix addition and scalar multiplication. You don't have to write all this down if you don't want to. Okay, note the similarities to what we have done in the past. If we have a matrix A plus a matrix B, we can switch the order and make it matrix B plus matrix A. Commutative property of matrix addition. Okay, commutative property of addition in regular algebra. Same thing holds for the matrix addition. Likewise, if I wanted to add A to B plus C, that's the same thing as taking A plus B and adding C to it. That's associative property. The parentheses, the grouping does not matter. Okay? If I'm taking 2 scalars times each other and then times A, matrix A, that's the same thing as taking a scalar times the product of that scalar times A. That's associative property. So it doesn't matter if I multiply the 2 scalars together and take it times the matrix, or if I take one of the scalars times the matrix and then take the other scalar times that result. It won't affect the overall result. Distributive property, I can add the 2 matrices together first and then take a scalar times it, or I could take a scalar times one matrix, the same scalar times the other matrix, and then combine the 2. That's distributive. And there's a second distributive that says that I can add the 2 scalars together first before I multiply it by the matrix, and I'll get the same result as if I took the scalar times A, the scalar times D, or the other scalar times A, and then combine the 2 by adding the 2 matrices together. So nothing scary to worry about as far as rules are concerned. They follow what we've been doing with algebra. Just formally telling you it's okay. Change the order, to distribute, to add out of order. I'm not going to quiz you over the names. I just want you to know the properties and that they work. All right, we good? All right, next slide. So if I asked you to simplify this, a couple of ways we could do this, right? we have 1/2 times a 2 by 2 matrix that has a subtraction of another 2 by 2 matrix. Based on those properties, we could distribute the 1/2 to every single element in both of those matrices, or we can do the subtraction first and then do scalar multiplication. I'd recommend doing the subtraction first, especially since they're not all even, and you'll have to deal with a lot of fractions if you don't. So if we do the subtraction first, we'll put our 1/2 out in front, and 2 by 2 minus a 2 by 2 is going to be a 2 by 2. What is, now be careful here, if it helps you to distribute that -1 to everybody and then add them, feel free, but you have to change the sign or you have to subtract every single one of these. So 8 minus 10 is -2. 11 minus 3 is 8. -15 minus 5 and 6 minus a -6, 12. This minus a negative is plus. Now we're taking our 1/2 times each of them. When we do that, we'll get what? -1, 4, -10, 6. So unless you're a glutton for punishment, you do the subtraction first before you do the multiplication, especially when it's a fraction. But if you really want to practice your fractions, you can. You get the same answer either way. Okay. Assignment.